Okay, in previous lecture on N-Point DFT part 2, we derived this matrix for 8-point DFT. 8-point DFT, that is 8 cross 8 matrix, and we calculated all entry based on this circle. So this method was explained in the last lecture part 2, and we enter all the values over here in 8 cross 8 matrix, and then we designated each column as D0, D1, D2, likewise D7. So 8 columns are designated like this. Now if we want to write DFT, 8-point DFT, then we have to follow the same equation that is there, the original equation of DFT. This is here capital N equal to 8. So if we follow the matrix equation, then we can write this in a short form, that is output is DFT, that is 8 cross 1 vector. Okay, each entries are designated as x0, x1, x2, so and so forth, x7. So 8 elements are there in this column vector, that is DFT vector, or you can say DFT values, 8 DFT values. This is a matrix. Now in place of these values, the columns, I have entered the columns. So you can write the same matrix in form of these columns. So all 8 columns are written over here like that. So it is 8 cross 8 matrix. Each column is of 8 elements. So it is 8 cross 1 column. This is also 8 cross 1 column. So there are 8 columns. So that is 8 cross 8 matrix. That is the same as this matrix that we have derived in the last lecture. Okay. Now if we apply this matrix on the inputs are nothing but 8 sample values, or a sequence of 8 samples, that is from x0 to x7, 8 cross 1. So we can write 8-point DFT equation into this form of the matrix. Okay. Now irrespective of the entries over here, we can decompose this matrix equation into this form, that is column decomposition form. That means when we apply this particular column, say this particular column entries will get multiplied by x0, d1 elements will get multiplied by x1, and so on. So what can we write? We can write this equation as x0 times d0, that is a column, d0 is a column. So x0 is a scalar, d0 is a column, that same column over here. Then x1 is scalar taken from here, that is the second sample value, multiplied by d1. And similar way we can write this as a summation of weighted columns. Okay, and they add up to a single column, that is nothing but 8-point DFT. Okay. Now what do? We apply decimation in time. So we take x0 sample, x2 sample, x4 sample and x6 sample together, okay, in one column. So if we separate out, so we can write x0 d0 plus x2 d2 plus x4 d4 plus x6 d6. So that is nothing but a matrix equation, that is 8 cross 4 matrix equation. 8 cross 4 matrix of d0, d2, d4, d6 vectors multiply by this vector, that is nothing but x0, x2, x4, x6. Okay. Same way we can separate out odd number of samples, that is x1 d1 plus x3 d3 plus x5 d5 plus x7 d7. And if we do so, then we can rewrite this as another matrix equation, that is having the columns d1, d3, d5, d7 multiplied by odd number of samples x1, x3, x5 and x7, that is 4 cross 1 vector. So 8 cross 4, 8 by 4 into 4 by 1, that is 8 by 1. So this is a column value. So the result is a column of 8 by 1, and another, this is also the result, that is 8 by 1. So 8 by 1 plus 8 by 1, that is 8 by 1. So that is the final result, that is 8-point DFT 8-point DFT value. Okay. Now we see, if we re-enter the values of D0, D2, D4, D6 columns from this particular original matrix, then D0, D2, D4 and D6 value, we simply copy it over here. We rewrite these values D0, D2, D4, D6 in this form, which is applied on this particular vector. So we will get this type of matrix. So it is 8 cross 4 matrix, the same matrix that we have derived in the previous step. Okay, and we copy the values of D1, D3, D5, D7 again. Then these are the values D1, then D3, then D5 and then D7. We copy this thing over here, then we will get this particular matrix, okay, which is multiplied by x1, x3, x5, x7, odd number of elements. Okay, so here these values are very simple. Okay, 1 1 1 1 1 minus j minus 1j. So that is the alternate column values in the previous matrix. If you see over here, it is 1 minus j minus 1 alternate column values, and other alternate column values will go into the other part. Okay, so they will come over here. Okay, now if we see this second part of this equation, that is the second matrix, then we can take e raised to minus j pi by 4 common. If we take from this row, say what will happen? See this. Okay, first we recognize this. What is this matrix? This matrix is 1 1 1 1 1 minus j minus 1j, and I have divided it into upper half and lower half. So first 4 rows, top rows and bottom 4 rows. So if you divide it, then this 4 cross 4 matrix is nothing but 4 point DFT matrix that we have derived in very first part. So that is the same over here. You can see this 4 cross 4 DFT matrix D4 we derived, that is the same as this, and lower part is also the same. So that is applicable on this 4 cross 1. So you can consider this 4 cross 4 matrix applied on 4 cross 4 one, that will give you 4 cross 1 result, a one column of 4 cross 1. Lower one will also give you lower part of the column, that is 4 cross 1. They are identical. Okay, because top entries and bottom entries are identical to each other. Say this is 1 1 1, this is 1 1 1, 1 minus j, 1 minus j minus 1 j, 1 minus 1 minus j minus 1 j, and same way over here you can compare. So we don't have to recompute the same entries. So once we compute these first 4 entries in the column, then bottom 4 entries in the column are identical to that. So it saves the computation. Okay, now look at over here in the second part. Say over here, if we take e raised to minus j pi by 4 common, then what will happen? It will give us 1 after taking e raised to minus j pi by 4 common, 1 minus j minus 1 j. That you can verify very easily. If you take if you do some paperwork, then you can find out it very easily. Now what is meaning of that? Suppose we do direct computation over here without taking anything common, then what will happen? This will multiply with x1, this will multiply with x3, this will multiply with x5, and this will multiply with x7. So that is going to be a summation. Now in this summation you can take e raised to minus j pi by 4 common. So if you take it out common, then what can you do? You apply the same thing. After taking this e raised to minus j pi by 4 common, the second row becomes 1 minus j minus 1 j. So if you apply this onto this and then multiply, that is the same. Okay, whether you multiply all the values correspondingly and then take summation, or you multiply these values and then multiply it by common factor. After taking the summation, you multiply by common factor, that is the same. You can verify this fact very easily. Okay, so what is the advantage over here? Say here you take matrix multiplication first and then multiply the result in the second place in the column by e raised to minus j pi by 4. Same way in the third row, you have to take this first element is minus j. If you take minus j common, then what will happen? This will become 1, this will minus 1, 1 minus 1. You can verify this 1 minus 1. So you have taken j common. So you first do this matrix operation and then multiply each corresponding element. So this element you will get one column as a result. In that the third place will be multiplied by minus j. So there is post multiplication. After computing this matrix, then post multiplication of the elements. Same way in this fourth row, you say first element is e raised to minus j 3 pi by 4. So if you take this common, then you can very easily verify this fact that the entries will be 1j minus 1 minus j, and that common factor that is taken out, that is e raised to minus j 3 pi by 4. Okay. Now what will happen to the bottom entries? So bottom entries, you can see this first row and this row after the, so this row and this row, you see they are negative of each other. So whatever multiplier you have taken out, only negative of that multiplier will do the job. Okay, do the same operation. Okay, so the if you can take this multiplier, only negative sign you take out and you will find 1 1 1 1 over here. Same way this e raised to minus j pi by 4, and over here all the entries are negative of each other. Okay, negative of each other. This is negative of this. So if you take simply that original multiplier in the second row was e raised to minus j pi by 4, here you have to simply take negative of e raised to minus j pi by 4. Okay, and then you will get the same entries over here. So you can see that over here 1 1 1 1 1 minus j minus 1 j over here. And what is the multiplier of second row? E raised to minus j pi by 4 in top half. In the bottom half correspondingly you get minus of this multiplier. So I want to show the fact that here the multipliers also have some relation. This multiplier and this multiplier negative of each other. This multiplier and this multiplier negative of each other. Same way you can verify for the third row and fourth row, the multipliers you have taken for third row, that is minus j. So here in this seventh row the multiplier is j, that is negative of that, and in the last row also the multiplier is corresponding to the fourth row, negative of that. Okay, so this is very important relation between the multipliers of top half and bottom half. So you don't have to do anything extra, because the top 4 cross 4 matrix, half matrix, top matrix and bottom half of the matrix are identical. You can verify 1 1 1 1 and 1 1 1 1. One second row and this row, they are identical. This row and this row are identical. So and their corresponding multipliers are also, post multipliers are also identical in a way they have negative sign with each other. So we don't have to do much of the computation. We can save much of the computation by doing in this structure. Okay. So this is this is the way of writing this equation. y0 to y0 to y3, that is top matrix, top half of the matrix will do. And as I told you, this 8 cross 1 result of the first half of this equation, this half part of this equation, that will give you this 8 cross 1. But what is the relation? y0 and y0. So that half of this, the same 4 values will repeat, that is shown over here. And in this second part, with including these multipliers, because they have these two are identical but multipliers are opposite sign, so what will happen? The result will occur in this fashion, that is v0 v1 v2 v3, but lower 4 entries are negative v0, negative v1, negative v2 and negative v3 likewise. So this is the way we can represent this matrix. So 8-point DFT is now decomposed into this 4-point DFT. This is also 4-point DFT, this is also 4-point DFT, and this is also 4-point DFT. So with the help of 4-point DFT, we can calculate 8-point DFT. That is the decomposition of 8-point DFT into 4-point DFTs. Now let us see what are the operands over here in this first half: x0, x2, x4 and x6, and what are the results: y0, y1, y2 and y3. These results are computed using 4-point DFT. Now in 4-point DFT, the input sequence is x0, x2, x4, x6, but in butterfly you have to again do decimation in time. That means x0 and x4 will come together and x2 and x6 will go into another butterfly. So that is shown in this figure: x0 and x4 and x2 and x6. So reshuffling of the data is required in this way, and the computed result for this is 4-point DFT. Okay, this is for this multiplier at the stage of 4-point DFT. It minus j is nothing but e raised to minus j pi by 2. Okay, this result was derived in the very first lecture, part 1. This was that was derived. So same structure we have utilized over here, that is for 4-point DFT, and the computed values are y0, y1, y2, y3 for upper half, and for the lower half the same values will repeat. So that is shown as a column vector over here: y0, y1, y2, y3, and again in lower half that will repeat. So it will become 8 cross 1 vector. Okay, plus the result of this, that is shown as over here: v0, v1, v2, v3, and negative of v0, v1, v2, v3, including that post multiplier. Okay, so that structure is shown over here. Now the inputs are x1, x3, x5, x7. They are in sequence. We have to reshuffle it in this way by taking decimation in time: x0 and x5 and x3 and x7. So x1 and x5 in one butterfly and x3 and x7 in another butterfly in 4-point DFT. But only this over here, you look at these points, this and this point will give you 4-point DFT, but we have to post multiply it by the corresponding e raised to minus j pi by 4. So we have done it over here: e raised to minus j pi by 4, then e raised to minus j pi by 2, e raised to minus j pi by 3, and the result will be out as v0, v1, v2 and v3. Okay, v0, v1, v2 and v3. So that is for upper half. What about lower half? We have to simply negate the values of that. What we have computed, v0, v1, v2, v3 we have computed. We have to simply take negative of that. That is not a big operation, so that we can simply negate the sign and we can rewrite. So this is the way we can decompose the matrix. Now we will have to combine these values and these values, because we have to create the lower half also in these columns, lower half of the columns. So in this case we have to simply repeat, and in this case we have to simply negate. So that can be done by butterfly, because what does a butterfly do? Simply multiply by 1 or multiply by minus 1, and we have to then add this value. So y0 will be added with v0, y1 will be added with v1, y2 will be added with v2, y3 will be added with v3. That is for upper 4 points of the DFT. For lower 4 points of the DFT, y0 minus v0, y1 minus v1, y2 minus v2 and y3 minus v3. So that structure we will see in the next lecture, that is called 8-point decimation in time FFT algorithm. That is that we will see in the next lecture. Okay, thank you very much.